about determinants. So So this is so-called Brack triangular matrix. See, so a matrix can be arranged in this way that so the A is n times n, okay, and B is n times n. And this one, 0, all 0 is m times n, and the C is m times n. So the whole dimension, this is n plus n, this is n plus n. Okay. And A is n times n, C is n. So the example is that if we want to find the determinant of suppose we have a determinant of 4x4 matrix, and we find that, by observation, we can decompose the matrix into 4 parts. So we see, okay, the left lower part is a 0 matrix. So then, by the theorem, we know that this is determinant of the left upper corner matrix times the determinant of the right lower matrix. Okay. And completely ignore this part. Completely ignore it. So it's quite easy to know that this is 3 times 5, that is 15. Okay, so we can compute the determinant quickly. And if you don't use this one, you can use the covector extension. Right? You can use the covector extension, but it takes more time to do the computation. Okay, so this should approve. Now, if C is non-invertible, okay, then the fifth matrix is also non-invertible. Why? Well, you see, when when C is non-invertible by row operations, because that the column, the rows of C are linearly dependent. So by row operations, we can get all 0 row, right? Remember that? We can after several row operations, then we can change the C equal to 0. But if we have a 0 here, then the whole 0 in the fixed matrix is also 0, right? So that this is the so we have so we prove that once we have a 0 by row operations, then this matrix is non-invertible. So if C is non-invertible, then this is also non-invertible. And so that the determinant of AB or C is 0. Okay? The determinant of A, the determinant of C. Because this is 0, right? C is non-invertible, so the determinant C is 0. And maybe determinant A is non-zero, but something like probably 0 is 0. So this is satisfied geometrically. Right. So when C is non-invertible, then we will have this one. Okay. So we prove the lemma. So now we assume that C is invertible. So by applying elementary row operations on the submatrix zero C. Okay, so we will apply the row operations on the submatrix. When we're applying the elementary row operations on the submatrix, it is the same as we're applying the row operations on C only, right? C. So return the submatrix C to its reduced row echelon form. Okay? Because C is invertible, so we know that any invertible matrix has reduced the echelon form, which is equal to the identity matrix. And then the determinant A, B, 0, C is equal to the determinant of C, determinant of because that determinant So we have, say, ABI, and do it one by one, okay? So, in the procedure, because that when we do the operations on C, on this submatrix, okay? When the operation is replacement, we will not change the determinant value, right? But if we do the row exchange, then we will change the sign. If we do the scaling, then we have to multiply the scaling. So anyway, so we can think about that. We will have, say, alpha 1, alpha 2, alpha k. Maybe we do k elementary row operation and the corresponding sequence, right? So we should keep booking a scalar there. So either alpha is just 1 because you don't change the value, or maybe some alpha is -1 because you do the row exchange, and some alpha is just the scalar you reduce. So when you do by row operations, you turn the invertible matrix into its reduced row echelon form. In the procedure, actually you multiply a lot of concepts here. And with the same row operations here, right? You should give the same record rate. Right? And the matrix becomes, because we didn't do anything about the upper half of the matrix, so it's right there. But when you do the row operation, because when you encounter all zeros, you change nothing, right? From our experience. If you exchange 0 rows together, that is also 0 rows. So all the elementary row operation will not change anything about the 0 matrix. And so we turn C into identity. Any questions? Just row operations. Whenever we look back, we want to see something big, we go to row operations. Okay? Any questions? Alright, so now, so what is this? Because the determinants of identity is equal to 1. Right? The basic axiom we have. So this product is just equal to determinant C. Okay? So we are satisfied to write down determinant of C here, and we have determinant of A, B, 0, identity. Okay? Up to here. Any questions? Now, we can do the big word substitution, right? By row operations. Because we have identity here. So that by the big word substitution, you can eliminate the whole D to 0. Right? Okay. So by applying replacement, and the only row operation we use is just replacement only. Okay? So by applying replacement row operations, to the rows of the submatrix AD, the submatrix AD by adding multiples of the rows of the submatrix 0 and identity. Okay, so we just do the replacement. The replacement is that we add the multiple of the rows here, the upper half, to the rows of the upper half, right? To cancel elements of D. Okay, we can do that. We can. This is called backward elimination. Okay, backward elimination. And in the procedure, because we use the replacement operations, so we will not change the value between them. Okay? So we can eliminate the submatrix D. Okay, so we can eliminate submatrix D without changing the determinant's value. Okay, so we have determinant AB, I. Okay. By applying the replacement elementary equation, we have A, and this is all 0, and this is 0, this is identity. Okay, so the determinant, this determinant becomes to this determinant. Any questions? No. Great. Now, again, if A is non-invertible, then again A 0, 0 identity is non-invertible. Okay, non-invertible. So that the determinant of A 0, 0 A times n is 0. And then the determinant of AD 0C, as we know that this is the determinant of C times determinant of A 0, 0, I. Okay. So this is 0, and this is determinant of C and determinant of A. Okay. Because this is 0. Okay, so we again get a 0 value. Now, the only test left to now assume that A is invertible J is invertible. So now A is invertible. So finally, by applying elementary law operations, okay, on the submatrix A and 0, the submatrix. So apply the law operation on the submatrix A0. Return the submatrix A to its reduced row echelon form. Identity n times n, and then so again, like this one, the determinant of A, the determinant of A0, 0 identity. Alright, so we apply the elementary law operations, including law exchanges, replacement, scaling on the rows in the upper half of the submatrix. When we do so, actually we do the same law operation on A. So we will have a beta 1, beta 2, etc. up to beta R, and we have determinant of identity. Okay, so we turn the matrix A into its reduced echelon form, which is just the identity matrix. And similarly, we have beta 1, beta 2, and beta R, and determinants of identity n by n, and the 0 and the 0, and this is identity m times n. Okay? Yeah. And again, this determinant is equal to 1. So we know that this product is equal to determinant A. Alright, so our conclusion is that A 0, 0 identity, right, is equal to determinant of A times determinant of identity, okay, and what is this? This is equal to identity m plus m times m plus m. So this is just the identity matrix, and so determinant is equal to 1. Okay, so this determinant is just equal to determinant of A. Alright, so finally, so that determinant of A B0 C is determinant of C, determinant of A 0, 0 equal to determinant of C, determinant of A. Okay, and we have that. Finish. So it's a little bit long, but the method I used just law operations and the basic axiom of determinants function. questions? Alright, so I will use the theorem to prove the lemma. This is a lemma to prove our main result. Theorem. The geometric multiplicity of an eigenvalue alpha of a linear operator E on an n-dimensional vector space over F no greater than the algebraic multiplicity of that eigenvalue alpha. Okay. So the scale field, you can consider vector space over real numbers or vector space over complex numbers. Fine, right? Depends on your interest. So the F can be the set of all real numbers, or the F can be the set of all complex numbers. Fine. But anyway, the geometric multiplicity, okay, of an eigenvalue alpha is no greater than, okay, the algebraic multiplicity of the eigenvalue. Any questions about the statement of the theorem? Okay, so we know, now I'll proceed the proof. Right? So suppose we can compute the eigenspace E alpha of the linear operator associated with the eigenvalue alpha. Okay? So with that, and with that, its dimension to be p. So p. Now P is the geometrical multiplicity by our definition, right? So P is the geometric multiplicity of the eigenvalue. Okay? And we find V1, V2 up to Vp, okay, and ordered basis for E alpha. Okay, so we have proved that the eigenspace is a subspace of V, right? It itself is a subspace. We proved that. And we know its dimension is P, so we can find an ordered basis, right, for the eigenspace E alpha. So, and the size of the basis is P, the same as its dimension, right? So V1, V2 up to Vp. Yeah. We now extend. So we now extend the linearly independent set. Because it's a basis, so it's a linearly independent state. V1, V2, Vp, to an ordered basis. For B, so we can extend it V1, V2 up to Vp, and then we can add one more, right? And two more, etc., up to the n. Okay, for V. Right? We know the procedure, right? Just add one by one. Okay, and this basis, of course, consists of n basis vectors. Right. So up to here, any questions? This is our preparation. So the first P vectors are eigenvectors of alpha because it's a basis vector in the eigenspace. So V1, V2 up to Vp are eigenvectors associated with the same eigenvalue alpha. And then we extend this linearly independent set into a basis vector. Yes. Okay? So now, to construct a metric representation of T relative to the basis P here. So we are trying to construct the metric representation. So before that, you can see things P V1, okay, is alpha V1, right? And P V2 is alpha V2. Up to T Vp is alpha Vp. Okay? As I said, V1, V2, Vp are in E alpha. Okay, so they are eigenvectors associated with the same eigenvalue alpha. And so we can see that. So this is alpha E1 plus 0. Okay? So that we can explain the function value by the same basis, right? And similarly, we have this is 0, V1 plus 0, V2 plus alpha Vp plus 0, V2 plus 1. Right? Things. So that the matrix representation of T relative to the basis B is T B, as we know, is T B1 T T V2 T, T VP P T VP plus 1 T T VN P. Okay, so this is the matrix representation of T relative to B. Now, TV1, the B coordinate of TV1 is what? It's alpha, right? And 0, 0, 0, all is 0. So what is this? Alpha 0, 0. Okay? And all is 0, 0. TV2, the coordinate, B coordinate of TV2 is 0, alpha, 0, 0. Okay? And up to TVP, 0, alpha, 0, 0. Now, starting from VP plus 1. In general, we don't know what's that, right? So in here, we just write down as we have a T and a C. It's general, so I don't bother to write it down. And so we specify the dimension here. So this is T and minus T, and minus P. Okay? So this submatrix is P times n minus P. So C submatrix n minus P times n minus P. And this corner consists of the zero matrix. So this matrix representation is block diagram. Now, so that the characteristic polynomial, okay, of T is f lambda is the determinant of P minus lambda. Okay? So this is the characteristic polynomial of this linear operator T. Okay. So that it's just this determinant. Right, and so what is that? This is the determinant of the matrix. And what is that? The whole thing here this one, right, is equal to alpha identity B times B. So we have entry alpha B times B minus lambda I B times B. Why? Because the matrix here can be composed into four blocks. Identity B times B. This is 0, this is 0, right? And here is identity n minus P times n minus P. Okay. So the identity matrix can be decomposed into block diagonal. And so when you multiply with lambda, it's lambda here, lambda is here. Okay? So that this corner, the difference is alpha identity P times P minus lambda identity P times P. Okay, and here we have P, and this is 0 for time. Now we have C minus what? Minus the lambda identity minus n minus P times n minus P. Okay, and so this is n minus P times n minus P. All right. So now, so we have determinant. Now we have a block triangular matrix. So by the previous lemma, the determinants of this matrix comes to be alpha 1 minus lambda identity B times P. And the determinant of C minus lambda identity minus P times minus P. Okay. So the characteristic polynomial F lambda can be factorized into two polynomials, right? One is this one, the other is this one. And what is that? This is the identity matrix, and you have a constant multiplier. So I'm not so sure. Is that a problem of our meeting examination or a quiz examination? I have forgot it. So this is alpha minus lambda to the fifth power, right? And the determinant of identity. Right? So this is this one. And this one is a polynomial G lambda. Okay? So this is polynomial G lambda, yeah? So we now have minus 1 is power, lambda minus alpha is power, and the G lambda. Oh, so maybe so that the characteristic polynomial is equal to minus 1 is power, lambda minus alpha, and the G lambda. Okay? Where G lambda is the determinant of C minus lambda. It's a polynomial, right? In lambda. Okay. So that lambda minus this linear vector is this power. is a divisor of F lambda. So this implies that the algebraic multiplicity of the root alpha of F lambda, right, is greater than or equal to P. Because that if you vector F lambda by the lambda minus alpha by linear vector, you vectorize them, then the number of vectors of lambda alpha should be greater than or equal to P. Because we already know this is the vectors. So that the algebraic multiplicity of the root of alpha should be greater than or equal to P. And this is equal to the geometric multiplicity of alpha. And we have that. So we finished the proof. Any questions? Let's prove the lemma for any block triangular matrix. The determinants comes to the determinants of this part and determinants of this group. Any questions? Okay, we take a break for 5 minutes. No product, vector space. Right? So the first section is about inner product. Before give a general definition of inner product spaces, I would like to spend some time to introduce a standard inner product. Alright, so the first one is the standard inner product. In Rn first, okay? In the real Euclidean space. Right? So the standard inner product of two vectors x and y, y1 up to yn in Rn is defined as so we use the triangular bracket defined to be x1, y1 plus x2, y2 plus So that is the definition. And so sometimes the inner product of two vectors n can be written in this way. So which is y equals x, or okay. I think for our data purposes, I think I keep this one. So how do I keep transpose? Okay, so this is the definition. So now the standard inner product is a function and it's a function. Okay, it's a function called from the Cartesian product of n to R, because the value of inner product is a real number. Okay, so this so the function itself will be denoted by this notation. So it has two arguments, right? One each from the n-dimensional Euclidean space. Alright? So it's a function. And this function, which has the following three properties. Alright? So for all x prime and y are n. Okay. First of all, call the non-negativity. It says that x is greater than 0 if x is not equal to 0 value. Right? So I think I give a beta formulation. So I would say x greater than 0 and x equal to 0 if and only x equal to 0. It's better the formulation. This is the standard formulation. So inner product of its, so you take the inner product of a vector with itself, then the value should be non-negative. And the inner product of x with itself is equal to 0 if and only x is 0. So together it says that if x is non-zero, then this inner product should be positive. second thing is symmetric. Alright, so maybe I will use that attitude, right? Symmetric. So we change the word into adjective, not the noun. Yeah, for consistency. Symmetric property says that x, y. So when you take this inner product of x and y is equal to y with x. Right, for real case. The third one, linear for the first argument. Okay, so that means that alpha x plus alpha prime x prime y. Right, so if the first argument is a linear combination of two vectors, then this linear combination with y to form the inner product is equal to alpha x with y and the alpha prime x prime with y. So it's called it's linear for the first argument for all alpha, alpha prime, and alpha. Right. So we have three basic properties for the. So you can check, right? You can check that by this definition. By this definition, you can check that this is true. Okay? So the proof that you have to prove, right? Immediately. So I just omit the proof because you need to prove the three properties from this definition. To prove the third property, it's better to use this matrix formulation. Okay? So now, the vector space n over R. Okay, together with the standard inner product. It's called the n-dimensional real Euclidean space. So when we talk about the vector space to be a real Euclidean space, when this vector space is together with the standard inner product. Okay, now for any vector in the Euclidean space Rn, the norm, or sometimes we call length, of x, so the norm or the length of x can be determined by iteratively applying the Pythagorean theorem as follows. So you can see that for n equals to 2, right? So now norm or the length is the square root of x1 square plus x2 square. And what is that? So this is the inner product. And we take the square root. Now for n equals to 3, the length is that because Pythagorean theorem. What is Pythagorean theorem? So in the plane, if we have this is x1, this is x2, right? And the length of this vector. So x1, x2 corresponding a vector in the plane, on the plane here. And so the length of this vector by the Pythagorean theorem. So you know this is 2, x1, right? So the hypotenuse, the length of the hypotenuse is actually the sum of the square of the two legs, right? The length of the two legs, and take the square root. So this is called the Pythagorean theorem because we have a right angle here. Okay, so from the Euclidean geometry, we can apply the Pythagorean theorem to find the length of the hypotenuse. So that is the formula here. And to find a vector in 3 dimensions, right? How do we do this in 3 dimensions? So in 3 dimensions, so we have a point here, so x1, x2, and 3, and then we have a vector. And we want to find the length of this vector. How do we find it? First of all, we do here, okay, and we have say alright, so this is x1, x2, and x3. Okay, on this plane, we focus on the triangle here. Okay, so so we focus on this triangle. But this angle here, this is 90 degrees. Okay, it seems that this is on the x1 and x2 plane. So you have this is because I have to put it into 3 dimensions. So actually this is a right angle, right? Right angle because we have a orthogonal coordinate system. So this is a right angle here, and so this is right angle. And now here, this is x2, this is x1. So the length here, this is the length of this vector. So the length is the square root of x1 square plus x2 square. Okay? And now, on the plane that this vector and this vector form a plane. And so now we have a triangle here. So now we consider this triangle. For this triangle, this is 90 degrees. Okay, this is 90 degrees. And so that this is the hypotenuse of the right triangle. So the length is the square root of the length here, right? So it's x1 square plus x2 square, x square plus x, because this part is x. Can you see that? So again, this is by the Pythagorean theorem. So this is square root of x1 square plus x2 square plus s. So now for 3 dimensions, the length of the vector can be computed by iteratively applying the Pythagorean theorem. One by one. Okay, so from the 2 dimensions, you go to there. So you know that this is your right. Okay, and again, this is square root x1 square, x2 square. And so this is x, y, xx, square root. Okay, you get that the length of the norm of the vector is the square root of the inner product of the vector with itself. So in general, so for geometric n into 2, that right? So I will write it down here. So it will be, we start with x1 square plus x2 square, square root, right? Now you apply the Pythagorean theorem again, and you take the the square root here. Okay, so you take the square root. Let me do it one by one, okay? So we take so this is the second time to apply the Pythagorean theorem. The second time. And the third time is that you square it, right? And you have to square it and then to do the square root. Okay. So you can do that. So continuously you can do that. Up to xn squared. And you take the square root. Right. So this is the generic formula. By applying this is what I'm saying, that we can try the Pythagorean theorem iteratively, one by one. Right. So moving to every time we consider only a plane, right? But the plane will change. Anyway, so you have that. And you can see that this is actually equal to alright, and so again, I give a proof that why the length of a vector x, the square root of the inner product of x with z. The reason why I want to give you the proof instead of give you a definition, because the textbook or many textbooks just tell you that, oh, you should define the length of the norm by this formula. Okay. And give you an illustration that for two-dimensional, this is true. And then you say, okay, this is just a definition. And everybody accepts, right? But I'm not a very good boy, right? No, I'm not an old man. Yeah. So I just want, why? I ask why? You are boys, but I'm an old man, right? So I have curiosity, maybe more than you, sometimes. Okay? And so why you give the definition this way? So the basic thing is that we have this definition is because we can prove that. Because we can apply the Pythagorean theorem iteratively, one by one, into high dimension, just like the procedure I illustrated to you. Right? So basically, this is the formula that we apply the Pythagorean theorem one by one. Okay, so now this is to give you the geometric feeling about the algebraic definition, because inner product, this kind of definition is algebraic definition. But you should connect algebraic definition into the geometric concept. Because the geometric concept we perceive is from the Euclidean geometry. Okay? Starting from the primary school up to the middle high and then to the high school. Right? We accept this concept gradually. So we have the point of view of the geometry of the world. Okay? And so we have the length, and then we have angle. Later on, I will talk about angle. Anyway, so this is the way we get this formula. You can take it as a definition, but I don't want it to do it. I want to illustrate that we can prove it by applying the Pythagorean theorem. Okay? And so now, orthogonality is an important concept in geometry, right? So we say that if two segments or two vectors form a rectangle, then we call that these two segments or these two vectors are orthogonal to each other. Okay? This is our concept in the Euclidean geometry. So now, but I want to derive the concept. How do we express orthogonality in terms of inner product. And once we know, then we will say, wow, inner product is so powerful. Because inner product is very simple, right? Very simple computation. But it will give us a lot of geometric insight. So I want to 7.1.2 is about orthogonality. In the real Euclidean space. Okay. So we let O, P, Q, three distinct points. In Rn, okay, with all the origin, so that the position vector x is going to be OP. Okay, so x is OP is the position vector of the point P. And the position vector y going to be OQ. So we have two position vectors, point to 2 points. So this is the position vector of the point P. Right? So these two position vectors, they form a linearly independent set. Okay, so here, this is a space, and the n dimension. Of course, we can't draw n-dimensional spaces more than 3, right? But this is the origin of the n-dimensional Euclidean space Rn, and we have 2 points P. Okay. So this is Q, right? And we have a P here. Okay. And so the position vector, this is X, this is Y. Right? So we have X and Y here. Now, and clearly in my drawing, X and Y are linearly independent. Because if they are linearly dependent, then they should be collinear. So the situation is that these 3 points are non-collinear, right? So probably I will see three distinct. Maybe I will use non-collinear points. Okay. So that these 2 position vectors are form a linearly independent set. Now the vector x determines a line, right? So it determines a line. Determine a line. Okay, and so this is a line here. And so the line consists of the Tx and T in R. So the line consists of all the points, the position vectors, right? All the position vectors. And so if T is positive, then the vector will be in the same direction as position vector x. But if T is negative, then it's in the opposite direction. So we have that. Now from the Euclidean geometry, okay, a point is on the line along has the minimum distance from Q, right? So has the minimum distance from Q, because a point x can be here, but the point x here, this point x, right, on the line, has the minimum distance, if and only the segment. So this is the segment SQ. So the segment SQ is orthogonal to the line. Yeah. Why? Okay, if x is not orthogonal, right, and this is orthogonal, right? So x is orthogonal, we have the right angle. Suppose we have another point, say T here. Okay? So that this is the segment TQ. Now, by the Pythagorean theorem, we know this obtuseness, right? The square of this one is the square of the length is the square root of the square, the sum of the square of these two lengths. So we know that the obtuseness has the length greater than the length of the leg. Right. Right. So this minimality, minimum property, is because of the Pythagorean theorem. Okay, and we know this fact from our middle high school. Right. So now that the only point on the line which has a minimum distance from the Q is that the segment SQ is orthogonal to the line. So this uniquely determines the SQ. Okay. So the orthogonality has this property. Okay, now so we want to find this point, right? So to find such a point. Let's relate Tx, right, be the position vector of S. Okay, so that position vector x in Rn. Okay, and now So the length of the segment SQ is equal to the length, right, of the difference vector. Y minus Tx. Because now this is Tx, this is Y, right? So this vector. So this vector actually, so this vector is just Y minus Tx. Okay? So this vector is the difference of Y and the Tx. Is that okay? The length of this so to find x is equivalent to finding t such that the norm y minus tx is minimized. Okay, so we want to find a t such that this norm, this length is minimized. Okay, so we have optimization problem, but fortunately it's an easy problem. Now since y minus tx is square, so we want to find a t that minimizes the length, the same as to minimize the square of the length, right? And this is, what is that? This is y minus tx and y minus tx. Okay, so the inner product of y minus tx is itself. Now by linearity and of the standard inner product, you already know that, how to do it. So this is becomes to y minus 2t xy plus t square. Okay. So by linearity, okay, you can write it down. Okay, now it's a projective function of t, so that we can take out like t squared minus 2t and x, y divided by x plus, so that the perfect squaring, so we use x, y, x square, okay, plus y minus x, y, x, okay. So this is the usual way to find the optimum t, right? To minimize the value because it's a quadratic function. So we use perfect squaring. So now we have T minus 那 y minus tx is meaningless. You can only t equal to xy divided by. So this is the quantity. Alright? So we found the t. So we find t. T is this one. Okay? So we conclude that the position vector OS, this is OS, of the point S, which has the minimum distance from Q is now, I have to erase it. For that, I think, so we have OS, it comes to x1 divided by x with x. Okay, so OS, the position vector of the point x is equal to this one. And the vector y minus tx, y minus tx is here, this one, y minus x, y divided by x in the product. So this one is vector, is orthogonal to the vector x. So this vector is orthogonal with this vector because the angle is 90 degrees. Okay, so now the vector x, y divided by. So this vector is called the orthogonal projection of y onto x. So this vector is the projection of this y vector onto the x vector here. The x vector is this one. So this projection. And we call this orthogonal projection because that the projection is going through this segment, and this part is orthogonal to x. So it's called a orthogonal projection. Right. And the important thing is that it can be seen that t equal to 0. T t equal to 0 if and only if x is equal to 4. Right? T equal to 0 if only if x equal to 4. Because when t 0 means that the point x is equal to 4. That means that the y vector is already orthogonal to x vector. So this is an only if y is orthogonal to x. Right? When q is here, so if you turn, rotate the q vector to here, then the x comes to the O, the origin, if and only if that the y is orthogonal to x. Otherwise, the t is non-zero. So t is 0 if and only if y and x, these two vectors, are orthogonal to each other. And what is t equal to 0? Is when the inner product is 0. So, okay, but t equal to 0 if and only x, y is 0. So we have a theorem. Okay, two vectors x and y, okay, in Rn is orthogonal if and only the inner product of x and y is equal to 0. So actually we proved this one. And but our textbook give this as definition because it's a long story. But I like to give you a long story. Why? Because it connects the geometric concept, right? You know, I demonstrate all this from the Euclidean geometry, right? The concept, and then gradually we find that wow, it's just going to say that the inner product of these two vectors is 0. But it's very easy to compute the inner product, right, of these two vectors. So it's very easy to identify two vectors, whether they are orthogonal to each other or not. This is the first theory. The second theory is a byproduct of this demonstration. Okay? It's called the Cauchy-Schwarz inequality. Is that the inner product of two vectors its absolute value is less than equal to the length of x multiplied with the length of y. It's called the Cauchy-Schwarz inequality. Why this is true? Why this is true? Look at here. We start with a square of the length, right? We start with this one. Okay? And gradually find that. So I use the same proof here. I start with this one and gradually up to here. Right? Okay? And now And so that this is greater than or equal to 0, right? Because this identity up to here, the length always non-zero, right? So this expression is greater than or equal to 0. Now I take t to be this one, right? So this becomes to 0. Because this is true for all t, right? This is true for all t. Is that correct? I haven't do any restriction for t. So the expression up to here is greater than or equal to 0. And now this one is minimized, right? Because only t is this. So I take t equal to this one. Now I start from here. So when I take t to this one, then this is kept, right? So I have y, and then y minus x y square divided by x greater than or equal to 0. This is true, still true, right? Because this is 0 already. So this is 0 and this part is greater than or equal to 0. And so y is greater than or equal to, or I just write down x y square x is less than or equal to y. Okay. And now x 1 square less than or equal to x times y. But this is the square of the norm of x. And this is the square of the norm of y. And now I take the square root. So when I take the square root, I have to have the absolute value, right? And I have done. So I proved an important theorem in the n-dimensional Euclidean space that we have the Cauchy-Schwarz model. This is very basic and important inequality when we study the geometry of the Euclidean space. And we are very fortunate, right? That to prove the fact, we have a byproduct of the Cauchy-Schwarz inequality. Okay. So now I write that because most of the textbook will use definition to give you the length of a vector, to give you how two vectors are orthogonal to each other, just by definition. But rather, I want to give you a proof or a demonstration how we end up with such a definition. It is basically just from the basic plane Euclidean geometry we learned from the middle high school. Okay, but we can't forget that in our life because that's so basic. Because Euclid developed the geometry from the intuition and take the intuition into an axiomatic way to give a lot of axioms, and from the axioms develops theorems, corollaries, a lot of things which form our geometric point of work. Okay, and it influences us so much, not only in the mathematical world, but also in the physical world. When you study the physics, even in the chemistry, the so-called basic pure science, you always have this geometric point in your heart, in your mind. Okay, so don't forget them. And they are all connected to linear algebra, especially the inner product. So that's why inner is so important. But we have to prepare for a lot part of the semester, and then we are able to go into the study of inner product spaces. Okay, so I will spend the rest of the semester to study the inner product spaces. Okay. All right. So I hope you appreciate this development, and I will go on next week. Okay. See you next week.